quantum computers are based on a different underlying hardware, which is a quantum bit. And a quantum bit has the ability to be in superposition, so it can be in a combination of the states 0 and 1, and then when you measure it, you only see either 0 or 1 with some probability. These quantum bits, you can let them interact through a quantum interaction in such a way that they get quantum entangled, and that means that overall you get this this complex state that's of all these quantum bits that can reach a much larger space of states than you can with a collection of classical bits.
Okay, welcome back to the Conjecture Institute podcast. And today I have with me Maria Violaris. And Maria is a fellow of Conjecture Institute, and her interest is in quantum physics and also quantum computation. But as well as that, I think she's the first proper science communicator we've had on. Welcome, Maria.
Yeah, thanks for having me on. Happy to be part of Conjecture Institute.
Great. Yeah, as I say, you're an accomplished now science communicator. You've been doing it for a few years, not only on your own YouTube channel, which I'll talk about in a moment, but at various other places as well. Your content has appeared and you've been trying to explain, in particular, quantum physics, but also quantum computation, quantum information theory, and a bunch of other things that we will get to. As I say, yesterday I was listening to your podcast. I was just binging a whole bunch of episodes. I can't recommend enough, if people are interested in quantum physics, to go to Maria's website on YouTube. We'll provide the link down below this episode so that people can really take a deep dive into some of the things that we'll only have a chance to really touch upon today. But if you're interested in the state of quantum computation, not only is Maria an expert in that area, but she works in that area as well, and has worked in that area. What your latest video there on YouTube is you explaining for almost 20 minutes about how you became a quantum physicist. So I thought we might go through that now, not for the full 20 minutes, but just a bit of an overview, because I've asked some of the other fellows that have come onto the podcast how they got into, especially if they've got a science background, how they got into science, and they often refer back to their school days. Is that where the passion for physics in particular began with you? Were there ups and downs as far as high school science was concerned?
Yeah, it did happen kind of during my school days. I had I guess a kind of an interest in science, and then a dip in the middle, and then an interest again. So for me, I was interested in it kind of in the primary school level, I thought. So that's kind of age, I don't know, 5 till 10. I thought science was cool and liked to do experiments and liked learning about science in school. And then in kind of early high school, I had a bit of a dip where I started to find science boring. I found maths boring. Some of those maths lessons at about age 12, I just found really difficult to get through. Yeah, so that lasted for a few years, and then it was reading. So I was trying to not choose as much science because we have options of how much science modules we can choose, and I was trying to do fewer and take music instead. But then for scheduling reasons, I ended up taking all the sciences on to the high level of exams and things. And then
do you mean, is that in year, like sort of the equivalent of the 11th and 12th year of high school kind of thing, where your final years of high school, is that what you're talking about, the electives at that stage?
Yeah, so we had our GCSEs, so the qualifications we do at like age 16. And then there's fewer subjects that you choose at age 17 and 18 for the final subjects. So this was at the GCSE level where you start narrowing down what subjects you're gonna go for. So that's where, yeah, I was gonna start moving away from science. But yeah, popular science kind of brought me back. I had some there were some popular science books just lying around at home that like my dad was reading, and then I'd kind of come across them.
Can you remember
And
any of
read
the
them.
authors?
Yeah, one of them was called 13 Things That Don't Make Sense. Michael Brooks, I think, is the name of the author. And that was cool because it wasn't just physics, it was kind of 13 things in general that are difficult to understand or mysterious. Um, and it's quite fun because it was written a while ago. There's a couple of the things that don't make sense that have now been resolved, or that yeah, some of the mysteries now do make sense. Um, but yeah, and then What Is Life by Erwin Schrödinger was another one. That one I found really interesting. And then yeah, also taking science to this high level in school, I actually started enjoying the later modules of physics a lot more than I had the science that we'd studied until that point. So then I started finding it interesting in school as well, and then was kind of combining that with reading outside of outside of that in like science magazines or a Plus magazine run by Cambridge University. It's an online magazine, and there were loads of really interesting articles in there that just kind of explore and got me excited about physics, quantum mechanics.
And so then at the end of high school, you obviously did well enough to qualify to, I think you said in your video, you were sort of tossing up at one point between medicine and physics. You ultimately chose physics, and then you went off to Oxford. So how did you decide, well, I'm going to do physics and I'm also going to go to Oxford University out of all the universities?
Yeah, I had this conflict of medicine and physics that was, so at the when I was around 17, I did some work experience in a hospital, just the children's hospital, and kind of spent a few days there shadowing some of the people there. And then shortly after, we had like a school trip to CERN, so I was kind of seeing these two sides of what the physicists are doing and then what people in medicine are doing. And then at some point, I kind of realized that I don't know, the studying you do for medicine didn't really appeal to me. Um, Even though I kind of liked the idea of the job and the career at the time. But I thought, yeah, studying physics for a few years would be a lot more interesting, and that kind of shifted me over to, okay, I'm gonna do physics, which was definitely the right decision thinking about it. Now, I wouldn't want to be a doctor, so I went into the right direction for me. Yeah, and then Oxford, I guess I wanted to apply to either Oxford or Cambridge to kind of push my work in physics as far as I could, and Cambridge offers a natural sciences course where you kind of choose different sciences. You don't specialize straight away to just physics, and I knew I wanted to specialize straight away to just physics as soon as I could. So the Oxford course was more appealing to me, so that's why I applied there.
And at that time, like when I chose to do physics, I was really only interested in astronomy and astrophysics. And it was only once I'd got to university and I sort of thought, oh, okay, this quantum theory stuff is really interesting. It wasn't even on my mind up until that point. Had you already decided at that point that you were going to focus in on quantum theory, or did other branches of physics actually even come into the picture, biophysics or whatever, or even medical physics?
Yeah, it's an interesting question. Yeah, I mean, I did enjoy the course as a whole, like all of the different aspects, and I think in terms of quantum, I was kind of conceptually interested in quantum, from this kind of reading before, so I was excited to get to that in the physics course, and then like a third of our second year course was a big quantum mechanics course. The first year was kind of laying the mathematical foundations, and the second year was when we really we kind of had three main areas, and then one of them was quantum mechanics. So I enjoyed learning about it there, although it wasn't until I discovered that the field of quantum information theory existed that I realized the actual parts of quantum mechanics that I like. So the quantum mechanics we studied in the course was more physicsy, whereas quantum information theory is kind of a level abstracted from the physics in a way, and it was kind of abstracting to the things that I find most interesting. So yeah, it took a few years for me to realize which bit of quantum is actually the part that I like. And then the other part that I was interested to get to in the course was thermodynamics, because I'd been reading about information and entropy and the second law of thermodynamics and the foundational issues to do with that, again in popular science. So I was kind of waiting for the thermodynamics course. Although again, the course, again in second year, didn't really kind of satisfy the aspect that I was interested in. And then I realised that there was an advanced philosophy of physics course, which wasn't something I could take in my course, but it was one that I kind of went to the seminars for fun, and I realised that their syllabus had the actual stuff I found cool about thermodynamics. And then yeah, third year there were quite a lot of kind of interesting areas, like biophysics was one of them that came into it. There were things to do with chaos theory and atmospheric physics. Yeah, a lot of kind of the more by that point it was more kind of exotic things in a way after laying the foundations in the second year of the core physics subjects. Which I found fun to kind of look into these different areas. But yeah, when I kind of figured out that quantum information theory was the part that I liked, it kind of yeah, kept me in the direction of the quantum. And I did actually do some medical physics work experience during my undergrad as well. So kind of again was in this medicine adjacent direction. Spent a few days at some of the hospitals in Oxford. But yeah, again was pulled away by by quantum in particular.
And then you did a PhD or a DPhil, I suppose it is, at Oxford, and you worked with Chiara Marletto, who chief scientist now at Conjecture Institute, among all her other accomplishments as well. And I think you worked on quantum thermodynamics. So you said just there that you're interested in thermodynamics. What the heck, for a layperson, is quantum thermodynamics as different from regular thermodynamics?
Yeah, it's a really broad field. The overall motivation is that thermodynamics was developed in the world of classical physics, and when we have systems that behave in a quantum way, that will change how things like what's possible in terms of like work and heat, and how you can transform these different types of energy and create engines. There's kind of a whole different landscape when the underlying physics is quantum. So the field of quantum thermodynamics exists to figure out what happens to the laws of thermodynamics when you're on that quantum scale, and then kind of what interesting things you can do with them, because it opens up this new space of, for example, using quantum entanglement as a resource for an engine, or extracting, yeah, kind of using quantum information as a resource, and yeah, there's a whole new space of things you can look at in these different contexts of thermodynamics. And then yeah, I had my kind of particular interest with Chiara, which was kind of focused on this approach from constructor theory.
And so the just regular thermodynamics, is it true to say that sort of it doesn't fit really well with the other kinds of laws, in the sense that like the first and second law of thermodynamics, they're not really laws of motion as such, are they? And does that pose a particular conceptual problem when you try and marry it up with quantum theory? Just the type of laws that they are don't seem to mesh very well?
Yeah, it's kind of odd sometimes even forming the question of what the laws of thermodynamics, what form they should take in quantum theory, because they have a lot of different forms in kind of classical thermodynamics, and then they're framed in this way that's quite detached from the physics itself in a way, or what the underlying dynamics of what's happening. So you end up with, there's a lot of formulations of the second law, and then there's a lot of so they're kind of based on different quantities like heat and work, and so depending on which formulation you use, it'll be kind of stated using a different quantity being referred to. And then there's also laws formulated from the perspective of statistical mechanics, which is trying to, in the classical world, kind of go more to actually pinpoint, like from the ground up, how these laws are emerging, and kind of more more embedded in the in what the laws in the dynamical laws, in a sense of looking at kind of how these behaviors are emerging from, like, having a lot of systems, and then a kind of large scale of having those systems. So there's a lot of aspects to kind of translating the laws in that sense. There's the more kind of statistical mechanical way of looking at things, of trying to go from the ground up, and then there's this these more axiomatic laws of thermodynamics, which are these kind of very general laws that are more that make these general statements, and they kind of pose different challenges to translate into the quantum setting.
Yeah, and now you're very much, you seem to be into quantum computation as well, and the potential there for the future of computing in general. But again, our audiences probably consist, there are going to be some experts listening, but a lot of people will be lay people. What's the difference between regular computation and quantum computation?
Yeah, so regular computation works using bits, so everything's encoded in zeros and ones, and the operations you do are flipping those bits between 1 and 0, 0 and 1, to do everything that the classical computers that we have everywhere are doing. And then quantum computers are based on a different underlying hardware, which is a quantum bit. And a quantum bit has the ability to be in superposition, so it can be in a combination of the states 0 and 1, and then when you measure it, you only see either 0 or 1 with some probability. You get this kind of projection into a single state when you measure the system. And these quantum bits, you can let them interact through a quantum interaction in such a way that they get quantum entangled, and that means that overall you get this this complex state that's of all these quantum bits that's kind of can reach a much larger space of states than you can with a collection of classical bits. And so what quantum computers do is essentially they use a collection of these quantum bits, they let them interact to kind of explore this huge space of states that they can explore, because they're these quantum systems that can be in these superpositions. And then you orchestrate your algorithms so that they'll explore that space in a useful way that you've directed, and then you kind of ensure that they end up reaching a kind of useful outcome at the end. So when you measure at the end and then you just get a single outcome, it kind of tells you something useful that would have been very computationally difficult to figure out just doing computation on classical bits, because you weren't able to explore that kind of huge space that you can with the quantum bits. So yeah, that's kind of the visual idea, I'd say, is the difference. And then physically you kind of build those quantum bits used in lots of different ways that people are exploring at the moment.
Now, in some distant, or maybe not so distant, in some future where we've got a universal quantum computer sitting in our desktop, is it true to say that if you want to use the thing in order to find the answer to some question, it's going to repeat the computation many times in order to generate a solution? Because if you just do it once, it'll come up with probabilities and you won't know which of the potential solutions is the real solution until you error correct by repeating it. Or do I have it completely wrong in phrasing it that way?
Yeah, that's right. That's usually the case, that you'll have to run it multiple times. There's you might have some kind of a probability distribution of outcomes that you will get when you measure the outcome at the end of your computation. And so if you just run it once, then you'll kind of just have this one point of the distribution, and then you want to run it multiple times to figure out exactly what that distribution is. Sometimes we're trying to characterize the actual kind of state at the end of the computation of the qubits, and that needs a lot of runs of running the computation and then measuring it, because you have to kind of measure the qubits in lots of different ways to characterize them, and a lot of times to kind of build up these statistics. So so that's something that we do when running quantum computers. We kind of set the number of shots, so the number of times that you run the computation each time, to be really high to give us enough statistics to kind of have a good idea of what that distribution of the final state looks like.
And there's a huge race on right now to actually build these things. And I find it really interesting for a couple of reasons. Like, one is, and you go through this in an excellent way on your channel. Again, I can't recommend it enough, because you take a deep dive into some of these big companies that are working on producing so-called quantum chips. This is going to be a long question because I have to try and figure out how to phrase it. But you've got, like, Microsoft is trying to build one of these quantum chips, and Google's trying to build one, and Amazon's trying to build one. So all these private companies. And it seems to me like over the years, periodically they announce that they've achieved something, that they've achieved a quantum chip or quantum supremacy, or it utilizes some quantum effect or other. Now, it struck me for a while that there's kind of like this weird tension in the field, which is kind of unique. Well, it's not exactly unique, because like the pharmaceutical companies have something similar, which is where there's a tension between the openness that normally goes on with scientific research, where people sort of share their results and collaborate and that kind of thing. But on the other hand, the pharmaceutical company, you also want to keep private the findings that you do have, in the hope that you can have something successful that you can then sell for a profit and fund, therefore, more research. And you compare that to somewhere like, like in cosmology or astrophysics, where one of the Nobel Prizes that was won was for the accelerating expansion of the universe. There were two teams that were competing, but they also ended up collaborating as well. So it wasn't like they were completely hiding their findings from each other. In quantum computation, it's like you've got both of these sort of things going on at the same time. I know down the road from where I am, there's a place called the Centre for Excellence in Australia of Quantum Computation, and it's this. It's got a lot of funding, like the federal government funds it, the American Army funds it, of all things. A huge consortium of universities and the private, funding as well. But they publish all of their stuff just freely out there, as far as I know. And so they're working, I think it's like ion traps or something or other that they're using in terms of like trying to physically instantiate these things. but it seems to me, from what I can tell, they haven't got more than about 4 qubits to be entangled to do very simple sort of calculations and that kind of thing. So when I personally, as a layperson, when I read articles about, well, Google's got a 64-bit quantum chip and that kind of thing, I think, but how does that add up? That surely would outperform absolutely every classical computer on the earth. Now, you go into some of this, and so, for example, I think you were talking about the Microsoft one, which uses quantum topology, which I don't know anything about, but you say in your video, you're a little bit skeptical to say the least. It relies on particles that haven't yet been detected. What's your feeling about these companies when they actually make these big announcements about things, but they keep the results hidden? They produce the glossy publicity and the pamphlet saying, we've achieved the thing, and the press release comes out, but the actual publication that peers can judge and assess the veracity of often doesn't accompany the glossy publicity. What are your thoughts on this entire thing that's going on?
Yeah, we're at interesting and evolving stage of the quantum industry, and as you said, there is this kind of tension between, to some extent, as a company, you want to keep your aspects of your work to yourself because that's going to be your kind of product at the end in the long term. On the other hand, there's this philosophy that kind of a rising tide lifts all boats, so that you want to that supporting the community as a whole is beneficial for everyone, and having this collaboration between different parts of the community and the industry. I think everyone kind of knows that you're going to need that to some extent, and so we have seen examples of industry putting a lot of resource into building that community and those collaborations. For example, at IBM Quantum, where I was working before, making videos alongside my PhD on an internship with them, they put a huge effort into kind of quantum education and creating a community for essentially for collaboration, and creating things like seminar series to distribute knowledge in the community, kind of with this view in mind that there needs to be an ecosystem in quantum that the quality of that ecosystem is going to benefit them as well as everyone else in the quantum industry. So there's that aspect. When there's announcements and then accompanying publications, we get different things happening in different situations. So the Microsoft case was a bit of an exception in a way. It was kind of a strange situation where people were and still are skeptical about some of the scientific claims around whether these new types of qubits, these topological qubits, have actually been detected or not. What happened at the time when they put that announcement out about that chip was that they had a paper out at the same time, but it wasn't about the results that they were talking about in the press release. But they were preparing a paper with the results that they were talking about in the press release for posting in the future. So that kind of created a bit of confusion about what have they actually shown. They're saying this, they've put this in their publication. But they did put out that other work afterwards in the future, and those works are going through peer review processes. But on that particular topic, there have been papers retracted from Nature in the past, so people are kind of extra wary, even when they have been peer reviewed, kind of exactly what the what the results in that area are showing. So that was a kind of unique case. In the case of Google, they for this kind of recent experiments that they've been doing on this chip, they at least for the one that I made a video about, where they demonstrated a milestone in the field of quantum error correction, which is going to be needed for future quantum computers. The paper about that milestone had come out as a preprint on the archive where people put their papers before they get published. That had come out a few months before the announcement, so the quantum community had already kind of seen that and thought it was nice, a great result. It had got lots of attention within the community, and then a few months later there was this kind of press around it when it got published, and then but it didn't come as a surprise for people in the community in a way, because they'd already seen the paper, seen the details, and it's something where there's a few cases where people are more open about things than others, and sometimes when a new device comes out or something, then I'm trying to like look at the specifications, how it's working, how have they managed to get this number of qubits, what are the errors, what techniques are they using, and there's scales where sometimes it's easier than other times to get to a certain level of detail on what they've done, and I think that's something that's still being balanced in the industry, is kind of figuring out where that line is of how much to share and how much to keep internally.
And what like, for example, the big companies or the big research institutes, insofar as they're working on quantum computation, are they working on like highly specialized quantum computers, or are they all universal quantum computers potentially?
Yeah, at the moment, all of them are pretty much going for universal computers, universal quantum computers. Although there are kind of techniques to make them specialized to some extent, and so, for example, there's some for certain quantum algorithms, you can think about what type of algorithm you're going to run on the computer, and then use that to inform, for example, your strategy of how you'll have the qubits connected. And you can, to some extent, optimize the different layers of the quantum computing stack, from kind of the hardware up to the software, for a particular application or algorithm in mind. But there's a balance of doing that because you can kind of reason it in two ways. You could say, okay, if I try and specialize as much as possible for a particular algorithm, then that'll be the fastest path to running this kind of useful algorithm, will be by specializing to that. But then on the other hand, we keep making new discoveries and developments on both how to run algorithms, but also how to kind of implement them on different aspects of the stack. Like maybe a new discovery comes out, and now you can use a different connectivity in your hardware to do that, to run that type of application. So you also don't want to kind of limit yourself too soon by making a design choice towards a particular algorithm. So I think because of that, in general, the community people in the industry try and build universal quantum computers, but with kind of algorithms in mind to direct how exactly the design choices are being made. But ultimately, it'll be universal quantum computers that everyone's trying to build. But they could look quite different for different. If you try and run the same application on different types of hardware or different quantum computing stacks, then it could run quite differently depending on choices that they've made on building that stack.
Again, this could be a selection effect bias on my part, because I'm not reading the journal articles, but I do tend to come across the popular science articles. And so one of the announcements that I have seen over the years is such and such company has achieved quantum supremacy, they say, only for a few months later for some other research group using a regular supercomputer to beat whatever the quantum supremacy thing was. What is quantum supremacy? Because if it's genuine quantum supremacy, my impression was that it couldn't possibly be beaten by any classical computer in a reasonable amount of time. So what is it? What are they talking about when they say that?
Yeah, it's kind of a fun aspect of the stage that we've been at the last 5 years with quantum computing. So yeah, it kind of started in 2019. October is when Google put an announcement that they'd achieved quantum supremacy. And what they had shown is that for a particular problem called random circuit sampling, which is kind of tailored towards being easy for quantum computers and difficult for classical computers. Um, and Yeah, and it wasn't claimed to do anything useful. This was kind of purely to show a difference in computational power for some problem. Um, so what they showed was that they could run this algorithm on a quantum computer um, in some kind of reasonable amount of time that would have taken a classical computer, an exceedingly long amount of time. And so they said they've achieved quantum supremacy, which is this line where a quantum computer runs something faster than a classical computer, even if it's not a useful problem. And there's a lot of different ways that people use terminology, but we tend to use the phrase quantum advantage to refer to the kind of the next milestone of doing something useful on a quantum computer faster than on a classical one. So that's kind of how I tend to see them, is that the quantum supremacy experiments are the ones that refer to these non-useful ones, and then quantum advantage is with that kind of more practical aspect in mind. So yeah, that announcement kind of first happened in 2019, and then even just a few days later, there was a response from IBM saying, no, actually, you can do that on a classical computer, without that much, without taking that long. And yeah, you can kind of get this back and forth with quantum supremacy announcements where they announce that they've done it faster than a classical computer ever could, and then these classical demonstrations come along and then beat the supremacy claim, and then you can kind of lose supremacy again. And the reason
Is
that
that?
can happen,
Oh, yeah, sorry, go ahead. Yeah, you go ahead.
yeah, yeah. So the reason it can happen is because when they do a claim of quantum supremacy, they've checked some particular classical methods for solving that problem and shown that those methods won't work for solving it efficiently. But there's nothing stopping someone coming up with another efficient classical method for solving that problem. They can't rule out that such a method exists, at least for these kinds of problems. So a kind of funny thing that has been happening in the community is that sometimes someone will put a quantum supremacy type announcement out, and then there'll be someone who works on the classical computing side who will go like, oh, that problem actually fits directly onto this kind of cutting edge method of simulation on classical computers that I've been working on. And then they can put out a paper, like a week later, doing a really efficient classical simulation because they're the world expert in classical simulations, and it happens that this new method that they've been working on maps exactly to this problem that the people used to do a quantum supremacy demonstration. So there's been that back and forth of you can lose supremacy after having it, but you can make that gap expand quite quickly just by adding a few more qubits. So we have kind of we are safely within the quantum supremacy zone now, and we have been for some years, even though this kind of race, this back and forth keeps happening. It's kind of understood that at least for these not useful applications, that milestone has been achieved and isn't really being questioned anymore now.
Uh-huh, uh-huh. So it's only for the useful types of things where sometimes the people working in classical computation come up with like a fancy algorithm that is actually able to more efficiently get to the answer than what the quantum attempts were. Is that a way of thinking about it? It's like a friendly arms race kind of thing between people writing algorithms and people writing algorithms, so quantum algorithm versus the classical.
Hmm. Yeah, so it was originally happening with these kind of not useful ones, and I say not useful, but even uh, since then, people have actually found interesting ways to use these types of circuit sampling algorithms. So that yeah, it's not to rule out that they could be doing something interesting, but yeah, they were originally developed just to show this gap. Um, but yeah, so that there was originally that kind of back and forth with the not useful side, and then it shifted to the useful side once people started kind of yeah, saying, look, I've done this simulation of a chemistry problem faster than a classical computer could. And so that created a new kind of back and forth of yeah, quantum advantage claims, because you then have this question of, yeah, have you done something useful faster on a quantum computer? And again, people will have these methods for simulating them that they'll say like, oh, I can actually simulate that. Um, and what I thought was interesting recently, I saw some papers come up that were demonstrating yeah, using cutting edge quantum computers for certain algorithms that were like yeah, interesting algorithms for with useful applications in mind. And I saw someone ask one of the authors of these papers, why didn't you call it quantum advantage? And uh, the author said that we kind of want to let the work speak for itself rather than making a big claim. Um, and I thought it was kind of a nice principle in a way of like, okay, you know, if we have done some great work that demonstrates this application faster on a quantum computer, then yeah, we'll let the community kind of um, understand that and be uh, excited about that rather than putting the claim first in a way, like yeah, letting the science get people excited about it.
Well, even the claim that some application or some use is useless is itself a form of like scientific prophecy. It reminds me a little bit of Hardy
Mhm.
and A Mathematician's Apology, where he was proud of the fact that he thought, being a pure mathematician, that most of his creative output was actually going to be useless for physics or elsewhere. But it turned out, not. I think before his death, in fact, some of the results he was finding were useful in electronics and stuff. So yeah, he was just saying, if you're a quantum theorist, that quantum computational theorist, that your algorithm is useless. Don't speak too soon, kind of thing.
Yeah.
Now, I'll move out of quantum computation for a minute, because I noticed you did a video with Vlatko Vedral, and among other things, you were talking about quantum cosmology. Now, I'm interested in cosmology. I don't know a whole lot about quantum cosmology. How does quantum physics inform cosmology? Because it's like you're marrying up the very smallest, well, usually regarded as the very smallest thing, with the very largest of things. So what's going on there?
Yeah, there's a lot of interesting questions it creates with cosmology. Yeah, it's not really my area of expertise, which is why I tend to interview other people about it on my on my podcast. But yeah, it leads to um, questions, for example, about the early universe. There's aspects of how we went from the Big Bang or whatever happened in the initial stages of the universe to what we see today, and then trying to explain that. Um, and it turns out that if you uh, use quantum mechanics, you can have this theory of inflation, where you have this kind of super fast expansion of the universe that happened between the Big Bang and what we see today. Um, and when you use quantum mechanics to kind of describe this early universe, you then can explain lots of the different features that we see that you wouldn't otherwise be able to explain. And so in that in that way, quantum mechanics is enabling these theories of how cosmology works, although they're very challenging to test. So there's this people, for example, in Vladko's research group, people like Aditya Iyer, so I spoke about it on the podcast with him as well, are thinking about ways that we can test for whether quantum kind of had a significant role in the early universe, and whether these theories could be validated, because at the moment they're just kind of theories without much testing that we've been able to do so far to validate them. But that's one way that quantum comes into cosmology.
So some of those things are things like, I don't know, like the smoothness of the cosmic microwave background. So the fact that the universe is 2.7 Kelvin and in every direction, and that's seems to be very finely tuned. But there's also anisotropies. There's very slightly warmer and very slightly cooler places. So both of those sort of things are mystery. Why so smooth, and yet why, not completely smooth, could be at least informed by a more deep research into the quantum, right?
Yeah, exactly. So things like explaining how different parts of the universe look the same, even though, they look kind of uniform in a way, even if they by a kind of standard classical model of physics, there wouldn't be a way for we don't really have an explanation for how they could look the same in different regions, because they would have been too far apart to have interacted in the past. So then you kind of need this theory of inflation, of this kind of unusual type of expansion, in order to explain how those distant regions could have possibly had a kind of shared causal past. And then quantum mechanics comes into explaining how that could have possibly happened.
All right, let's move from inflation to information. You've worked on the physics of information with Chiara Marletto. What is information? I think most people would just think, well, information is the stuff that you find in books in a library, or, what you type into Google, you're looking for information. So what on earth can physics add to this understanding of information?
Yeah, it's interesting, kind of this translation of the everyday concept of information to then the way it's used in physics and computer science. And the kind of computer sciencey way of looking at it is to consider information as being what you kind of encode in bits that can be zeros and ones, and then you have these kind of strings of zeros and ones that you can use to encode information, at least in a kind of binary way of if you have something that can be a 0 or a 1, then it's a bit, and you can consider traits, or like adding more levels to that, where you can have 0, 1, 2, for example. But to kind of simplify things, and because of the way that computers work as well, based on bits, we tend to think about things in terms of bits. But then there's kind of this more fundamental sense in which information comes into physics, and that's kind of motivated this work that Chiara Marletto has been doing on trying to bring information into the laws of physics in a fundamental way. And so Chiara, along with David Deutsch, has been developing this theory, constructor theory, which aims to express laws of physics with statements about what's possible and impossible. And this is kind of naturally lends itself to expressing laws about information. So when you consider a bit, for it to carry information, it has to have a kind of counterfactual property that it could have been in a different state. So if you have something that's in the state 0, then it must be the case that it could have been in the state 1. Otherwise, it's not carrying information. It's just kind of a system in some state. And so that kind of then links to statements about possibility. You have to say, okay, even though it's in the state 0 right now, it is possible that it could be flipped to the state 1. And so in this kind of constructor theory setting, you can then you have statements about what's possible, and you use them to define information kind of implicitly by defining what kind of systems can carry information. So then you can say a system that can carry information is one where it's possible to change its state from one to another for at least 2 different states, to kind of change from say 0 to 1 or 1 to 0. And you have to be able to kind of go back again as well. So you have to go from 0 to 1 and from 1 to 0. If you can only go from 0 to 1 and not 1 to 0, then that also doesn't count as an information storage system. So I think of information kind of in these terms of thinking about different devices being able to kind of satisfying these properties for being able to store and manipulate information, and then these things that we consider information in everyday life, like books, films, any kind of content, you can kind of translate on some level to being stored in different information media that satisfy these properties.
Do you have a view on, this is a popular science kind of question, although physicists have debated this for, I don't know, the better part of a century now, the fundamental nature of reality. Does constructor theory have anything to say about this, or do you have an opinion either way? Is the fundamental nature of reality information, or is it physical, or doesn't that question make any sense?
Yeah, I think information is fundamental to reality in a significant way, I guess, in a at least for some level of explaining a large portion of aspects of reality. I think information is kind of where you get to as your fundamental aspect. So in a similar way, in a sense to how energy is a kind of significant fundamental property, I think information kind of has that status as well.
Does the universe itself, or does physical reality come from information, or is information the emergent thing from, let's say, laws of physics or something else? Or again, does that question not make any sense?
I think information is, I wouldn't say it's, I'm trying to think if I'd say it's emergent from the laws of physics. I think it's kind of part of the laws of physics, and so it's, I think it's part of the fundamentals of what we need to account for the range of physical phenomena that we see. And so if you don't see information as fundamental, so I think some people could take the view that that when you're considering things like whether a system could be in one state or another, that's not really a fundamental question, because the fundamental physics is kind of, say you're storing this information on a coin, the fundamental physics question is about like the particles of that coin and what trajectory they're following, and that's the real physics question. The real fundamental thing is, say, the quantum state of that coin, for example. Whereas in my view, the fact that coin can carry information is kind of a fundamental aspect in its own right, and there's fundamental laws about information and how it can transfer between systems and what it can do, kind of in their own right. I'd also be hesitant to say that everything else emerges from information in the sense that, I think at least the way I see it, there's a kind of information level of explaining things, and then there's another level of explaining things in the sense of, say, knowing the or figuring out the quantum state of that coin. And there might be a kind of information theoretic style arguments or laws that you can pose that will end up constraining that kind of underlying dynamics of your system, in such a way that I guess you could see that type of physics from dropping out from this kind of more information type statements about what's possible and impossible, these counterfactual statements. So yeah, maybe in that sense you could imagine kind of the other aspects of physics dropping out from an information-based laws. But yeah, I think at least in terms of actual information that's stored in systems and transferred between systems, I kind of see it as a sector of fundamental physics rather than being, say, the core of the whole thing in a way.
Yeah, there might be some questions from the audience that I'll get to in a moment, which touch on that. But I've got one final one from me before we do that, which is, what's the latest with you career-wise? What are you researching and who are you working with at the moment?
Yeah, I kind of think of myself as doing 4 strands in a way at the moment. So I work at a company called Oxford Quantum Circuits, which is a spin-out from the University of Oxford that builds superconducting quantum computers. So I started that job after I finished my PhD last summer, so it's been about a year now. And in my job I have a hybrid role. So I partly work on research in the theory team, and that's on the field of quantum error correction. So my team is trying to figure out how to essentially how to build the next generation devices with superconducting qubits, what kind of strategies to go for with reducing the errors on those devices. And then the other aspect of my role is on the communication side. So I work with the marketing commercial teams on, for example, making content for different audiences, and more generally bridging the technical and non-technical sides of the company and kind of translating for example the company narratives, integrating those with the developments in the technology and making sure that comms are accurate and also reflect this kind of broader narrative, while also explaining what technical developments we're having, and then also kind of represented the company at events and giving talks and things, which I enjoy. And then alongside that, I've kind of got my personal content creation, like my YouTube channel. I do some kind of occasional freelance science writing, like an article for Physics World earlier this year, for example, about the quantum eraser paradox. So that was kind of in this quantum foundations area. And then I've wrote an article about time loops for Nature when they were doing a segment on quantum myths. So kind of have a few of those things happening. And then continuing my personal my projects in quantum foundations research of themes that I was looking at in my PhD. So I have ongoing research projects on that as well. So that's kind of my general landscape. And then I'm I guess going forward, one of the things I'd like that I'm working on is writing a popular science book to kind of demystify quantum. So that's something that it's kind of one of my longer term projects that I'm working on.
Is a key part of that just taking seriously the Everettian interpretation, so to speak, of quantum theory? Does that resolve a bunch of these issues that people want to talk about when it comes to paradoxes and various things?
It does. So I kind of realized when I was making this quantum paradoxes series in this internship I had with IBM. I made a series of videos called Quantum Paradoxes. They're quite technical. They're looking at mapping paradoxical thought experiments to quantum computers and kind of to quantum circuits that you can run on a quantum computer as kind of toy models in a way of things that you can run on near-term devices. And my motivation was that you can kind of resolve the apparent paradoxes by viewing them as these programs that you can run on a quantum computer. It's kind of a nice way of seeing concretely what these thought experiments are saying, then seeing how it gets resolved. And I thought it was funny doing like, I think maybe 14 of these videos on completely different sounding thought experiments. And all of them had this kind of unifying factor of that you resolve the strange aspect of the thought experiment by treating the measurement device as a quantum system, which is the assumption of this Everettian theory, is that measurement devices are quantum systems and measurements are those systems getting entangled with whatever it is that they're measuring. So you kind of describe everything in this quantum way, and that resolves kind of this whole family of strange phenomena that you get in all these different sounding contexts. So that is something that I want to get across in this book, is kind of that quantum mechanics makes sense in a way. So yeah, kind of I want to explain the core kind of phenomena in quantum, and then kind of how they relate to today's technology, and then resolving these problems, but also how we're using quantum in technology today, and then kind of a look to the future with all the different ways that there is loads of open problems with quantum physics still, even though some of these typical paradoxes can be resolved. So I want a segment on this problems of quantum gravity in space-time, and open problems with quantum theory and the future of technology as well. But yeah, part of the focus will be to demystify and resolve some of those problems that many people think are actually open problems, but at least if you find these explanations compelling, they are solved problems.
Yeah, very good. That's really exciting. It's good to hear. I'm looking forward to your book, whenever it comes out in the future. Let's go to some audience questions that we've got here. We'll see if we've got enough time left to get through them. First one from Aaron Stupple, board member of Conjecture Institute. He asks, I get how the waves of photons interfere. Light is a wave. How does interference happen with other parameters, position, momentum, spin, as occurs between the masses in superposition and interferometer? I don't know if you got that.
Mm-hmm. Yeah, so thinking about how things like a mass can interfere as opposed to the more typically wave-like systems like photons. It's an interesting question, trying to visualize and understand how these interference phenomena work. So in the case of photons, we have that they're kind of these particles of light, and we I guess more generally in quantum physics, we have the case that any system is going to have a wave function, and that's going to be its kind of wave-like, that'll determine this wave-like behavior. So in the case of photons, each individual photon, even though it appears as though it's a particle in a sense of being an individual photon, it has this wave function, which then means that it can interfere with itself, and that can lead to kind of an interference pattern on the screen of a double slit, or in a the branches of an interferometer. And then if you replace that photon with instead an electron, which then has mass, you will still get an interference pattern, because that electron also has a wave function, and you can then get interference happening again with itself. And then the more mass you add, the more difficult it is to control and manipulate that wave function. But as far as we've seen so far, there's no limit to how far you can put larger and larger systems into a interference experiment. And then there's another aspect of kind of what degrees of freedom you're interfering. So when we put a photon through a beam splitter, you're splitting it into two different pathways, into a superposition of going down those different pathways, and then you can re-interfere those different pathways. So that's this kind of position degree of freedom, because you're literally moving it you're putting it in a superposition of different regions of space and then re-interfering those. And then by creating a different device to do the kind of splitting and the re-merging, you can do that with other properties, such as polarization, for example, is another property of the photon. It can be polarized in different ways, and then you can put components that then let you interfere that kind of polarization degree of freedom instead of the position degree of freedom. I'd think of it in a way as what determines what you're interfering is kind of what devices, what equipment you have. So if there's a particular property and you want to do your interference with that property, then you'll have to build your equipment, build your experiment to be sensitive to that property and manipulating that one, and then getting that to kind of put your system in superposition and interfere it in using that property. And position is a kind of quite a nice visual one, but there's many other properties that we use across different types of quantum systems.
Now, Hugo Graw has 3 questions, so feel free to do these very rapid fire. His first one is, when did you first come across critical rationalism, and how did that influence your research?
I probably came across it from another Conjecture Institute fellow, Sam Kuipers. I think I saw some discussion about X handles recently, including your one, Brett, on whether you change it or not. And I think Sam's, before he changed it, was like crit rat or something.
That's right. Yes, it was.
Those lines. And yeah, that's what it was at the time where I first met him from, because we were both doing a PhD in the same research group. So probably from our conversations is when I kind of first heard the terminology of what critical rationalism is, while wondering what this crit rat handle is and so on. Kind of found out what people in that community kind of think about, including not just physics, but things like education being a big theme that is discussed, and AI and questions around that. And then during lockdown, kind of started reading loads of popular science books during COVID. So that's when I read David Deutsch's books, The Fabric of Reality and The Beginning of Affinity. And they've had a big influence in the critical rationalism community. And then I found them very interesting, and they changed the way I think about some things. And then so I guess that kind of relates to what I understand from critical rationalism, as well as the kind of backdrop of where some of the ideas in that community come from.
Do you have any thoughts on Eric Weinstein's theory of geometric unity?
I haven't really. It's not something I've looked at myself. I've seen lots of back and forth discussion about it on social media with different people saying different opinions on it, and a kind of broader discussion about the way that science is done with yeah, people going back and forth on yeah, whether it's kind of being rejected from the scientific community or kind of unfairly, or yeah, issues around that. But yeah, the topic itself isn't something that I really know about. So yeah, I'll just kind of leave that for people that yeah, more into that area to tell me whether it's interesting or not.
What does your learning process look like when you want to learn something new? Do you have any special tools or techniques that have been successful to you or for you?
Yeah, I don't really have particular techniques now. I think because when I was in education, like doing exams and things, I had a lot of techniques and strategies that I'd use to learn things in that context. And then the next stage was kind of my PhD, um, in which case I'd learn things from reading papers would be the main thing for kind of learning a new area. I'd read papers, go through derivations myself to make sure that I understand them. Um, I suppose I sometimes think that that one way you could approach learning a new subject is to kind of go from the ground up in a way of doing like a full mapping of that area, and maybe going through like a whole course or a textbook and kind of working through systematically, which I think can work really well for some people. But for me personally, at least in recent years, I tend to have been kind of learning more on a needs-based basis of like what I've needed to use, and then kind of learning the background that I need for, say, understanding a particular problem, or understanding a particular paper that's interesting. Kind of starting from that and then finding the background that I need to understand that thing. Just because the space of things you could possibly learn is so large that I find I need something to kind of focus what I'm learning.
It's almost like that's the ideal, rather than having things foisted on you by someone else. You know, if you have your own problem, then you just do the learning needed to solve the problem.
Yeah. Yes.
Okay.
Yeah.
From Meeson, I think is the way they pronounce their name. Asking you to engage in some prophecy. How far are we from building universal quantum computers?
Yes, as you say, it's a prophecy of you can't predict the how science and innovation and progress will develop. But it's interesting. The last few years and recently, organizations and companies in the quantum industry have been putting out roadmaps of the plans for when different scales of quantum computers will be built. So, including the company I work for, Oxford Quantum Circuits. So, yeah, it's quite exciting and ambitious to kind of attach these years to when we're going to build a particular device. So, you can have a look at that roadmap as an example where so there's different scales of quantum computers because you can build them at different error rates. So the first kind of error rate that people expect the first useful applications of quantum computers to come from is 1 in a million. So kind of being able to run 1 million quantum operations, and that's a device that the community is aiming to build by the end of the decade, I'd say. In terms of different companies and governments as well, are trying to ensure that a computer of that scale exists by the end of the decade. And then early next decade is the ambition for building the next stage of billions of quantum operations, and then trillions of quantum operations is the one after that. Again, in kind of early 2030s is when people are aiming for that. And that's the scale of quantum computer that should be able to run Shor's algorithm, for example, which is the famous algorithm for breaking cryptography, which, yeah, got everyone excited about quantum computing in the early days of it. So, yeah, I guess broadly within the coming decade, people expect to see this transition going initially to millions, then to billions, then to trillions of quantum operations.
Bad news for you, unfortunately, Maria. You may not have read the AI 2027 paper, but I did, and the world is ending due to artificial superintelligence in about 2030. So I don't think we'll get to trillions of quantum operations, unfortunately. Another question here is this is an interesting one that I think is unresolved, but what are your views on whether or not the human brain is a quantum computer of a kind?
Yeah, I mean, there's definitely a lot we don't understand yet about how we run as programs on our brain, or how that process works, and how far the physics of the brain is involved in our consciousness and our experience. It seems to me that quantum kind of non-trivial quantum effects, in the sense of things like superposition and entanglement, that I don't see a reason why they would be needed to explain consciousness, for example. I think I imagine quantum mechanics will definitely have to be taken into account in the same way that it is in, say, all of chemistry, just because the brain is ultimately, there's important processes happening on small scale, and at those scales, the using quantum mechanics to describe them will be required in order to have accurate descriptions of what's happening. But I think often when people are thinking about this question, they're thinking more about whether there's a kind of more non-trivial way that quantum is affecting consciousness, or is involved in maybe in the similar way to how a quantum computer is actually manipulating kind of quantum bits, in a sense. Yeah, I'd say my intuition would be that it doesn't require manipulating kind of quantum bits to operate, but it could be the case, and it would be really cool if it is the case. So it's definitely an interesting question, and one to consider. How we might work towards testing it, and I think it would be really exciting if we do manage to understand consciousness and build quantum computers to actually start, even if our brains don't operate as quantum computers, to kind of create brains that do operate as quantum computers, or at least with some quantum computing element, and then do experiments with putting people in superpositions and seeing what the conscious experience of being in a superposition is, and this kind of huge space of things we can play around with that.
That's David's thought experiment, or potential experiment for testing the many worlds against the collapse models and that kind of thing. When we have quantum computers, which domain will they revolutionize the most? Physics, AI, or knowledge itself?
I mean, all of them. They could, in principle, revolutionize. Probably, I mean, to me, it seems like if they revolutionize physics, then that'll have knock-on effects on everything else, because you could kind of create a feedback loop of, if you manage to discover new physics, then you can create even the next generation of technology, whatever that is. I don't know, maybe it's computers that somehow account for quantum gravity, for example. If you've discovered a theory of quantum gravity through the the help of quantum computers or some of the experiments that you can run on them. So yeah, my intuition would be that that's where that if it provides advances in physics, in fundamental physics, in the long run, that's kind of what would have the biggest ultimate impact through this kind of feedback loop of everything that would then lead on to, including the new types of knowledge that you can create, and potential impacts to, I guess, future versions of AI or whatever AI becomes in that new setting.
Peter Ramkissen has posted under our post, after 2 years, I'm still trying to understand this paradox. And he links to a YouTube video from you about Newcomb's paradox. Now, I have to say to Peter, that's technically not a question, but can you help Peter understand Newcomb's paradox?
Yeah, so Newcomb's paradox is a thought experiment where you're kind of in this game show context in a way, where you have these two boxes that you can choose to take away with some money, and one of them has, for example, £1,000 in that you can see the box is open, you know that there's that money inside. The other box is shut, so you can't see what's inside. You're told that there's either £1 million or nothing in that box, and then you're asked whether you want to take both boxes home or just one of them. The twist is that there's a predictor that predicted which box or boxes you would choose. And if they predicted that you would only choose the one that may or may not have 1 million, then it put 1 million in it. If it predicted that you would take both boxes, then it put nothing inside that mystery box. And this leads to a paradox, because there's two kind of seemingly rational ways of reasoning about what decision you should make. One is to say, well, no one can change what's in the boxes now, regardless of what the predictor predicted, so I should take both boxes, because otherwise I'm definitely leaving behind £1,000. The other form of reasoning is to say, well, this predictor has always been 100% right, so in that case I should just take the one that may or may not have 1 million, because then it'll have 1 million in it, because that must be the case to be consistent with my choice of choosing the one just taking that box, and the predictor's going to be right. And then there's a solution to this paradox that I read on the Constructor theory website, from a note that David wrote, which I found really nice and satisfying, which kind of inspired this video for David's 70th birthday. And I'd actually read about this thought experiment back in a book when I was a child, called The Pig That Wants to Be Eaten, and has a load of thought experiments. So it's something that had puzzled me for a long time, but then I kind of found this solution, and I was like, oh, that's cool. And what the solution is that kind of David presented, or the type of solution is to say that in order for the predictor to predict exactly which decision you would make, they would actually have to create a simulation of you to simulate your exact decision-making process. And in that case, you would, when you're making this decision, you have no way of distinguishing whether you're the real you or this simulation that the predictor is using to decide which version of you, to decide which decision you'll make. And so you should just choose the one box, because if you're the simulation of you that the predictor is using, then you should just choose the one box so that they'll put 1 million in it, and that'll be the best benefit to you, or be if they put 1 million in the box. That's what I find a nice, satisfying resolution to the paradox.
You can apply that to, this is something I've been rattling on about recently, this whole issue with superintelligence going to take over the world. So Nick Bostrom originally wrote the book Superintelligence, and he said, consider the thought experiment that you've got this superintelligence that is doggedly committed to converting the entire universe into paper clips, never mind the reason. Now, people say, well, you could just switch it off. And he says, aha, but it's a super intelligence, you see. It can always predict what you're going to do. It can always thwart you. So before you get to the PowerPoint and switch it off, it will think of that because it's simulating yourself. Or rather, he doesn't put it that way. He just says that it's smarter than you and can always predict you. So applying David's reasoning to that scenario, the only way it could be a perfect predictor of you and everyone else on the planet is to actually run simulations of you and everyone else on the planet, in which case it would have to be a person. It'd have to think creatively like a person. And so it wouldn't be doggedly committed to converting the universe into paper clips anymore once it runs that simulation, because it'd be a person. So yeah, this way of looking for the hidden assumptions in these kind of paradoxes is absolutely crucial to undoing the Gordian knot kind of thing. Now, just two more questions, I think. Oh, someone has a two-part question, because I know you have to go to your meeting. Sparsh Mathur asks, it was a long one, but how are information computation and transformation related? What distinguishes computations from other transformations?
Yeah, I guess in some way, transformations are kind of a broader set of things you can do compared to computations. So transformations in a very broad sense can include things in the physical world, like transforming, let's say you have a chemical reaction turning some initial substances into some final substance, as happens in a chemical reaction. That's a type of transformation. But there's many of those that have no sense in which they're a computation. So I guess a computation, I don't think I have a nice succinct phrase to define what it is, but kind of the essence would be that it's manipulating information in a way that's then telling you some useful answer to a question via an algorithm that's known to lead to an answer based on some input. And I think you can map different kind of physical types of transformations. You can probably consider ways that you could turn them into a computation by by embedding kind of an algorithm into it somehow, like some logic. I guess that's kind of how the computation aspect comes in, is in having that logical manipulation of information happening within whatever physical transformation is happening.
His other question, I think we can dispense with. He asks, what's the difference between universal Turing machines and universal constructors? Universal Turing machine is just a computer, so it's going to compute things. So it could compute, for example, the trajectory of a bullet coming out of a gun. A universal constructor can build anything that you can write the program for, so it could literally build the gun and the bullet, and never mind computing its trajectory. But the final question, let's just go to Neil Hudson. He has asked, can you please explain in simple terms what are the costs of enforcing logical reversibility in classical versus quantum computation in terms of energy, memory, and practical implementation?
I guess, so with reversibility in classical computing, usually we compute in a way that's logically irreversible. So information is kind of in a sense getting lost because we're not keeping track of everything. And according to Landauer's principle, that when you erase information, there's a kind of minimum entropy cost. There is a kind of a small amount of irreducible heat that's dissipated because of doing that logically reversible classical computation. But in practical terms of today's computers, it's not a limiting factor, and compared to the rest of the energy scales involved in running a classical computer, the energy scales of this kind of Landauer heat dissipation are very low. So then for a normal classical computer, they're not yet at a relevant scale. in quantum computing, you have this kind of intrinsically reversible structure, because every quantum operation that you can do, you can always do the reverse in order to have a universal quantum computer. So it's kind of, yeah, intrinsically reversible. You still end up having to do irreversible things essentially every time you do a measurement. Then you can't reverse that within your quantum computer. And so in the process of reducing errors in quantum computers by doing quantum error correction, that involves bringing in a load of extra qubits that we are then going to kind of measure. And so that even though we can effectively create this reversible quantum computer, in practice we are doing a load of irreversible operations in doing that, which have their own entropy costs, again in this kind of Landauer type way of, in order to reset something to a blank state, you've got to have some kind of minimum entropy cost. So yeah, so that process is happening in quantum computing as well, as we try and we have to keep feeding low entropy into our computer by bringing in kind of blank qubits in order to keep this this process going, and then kind of dumping out our entropy that we're creating.
You've been very generous with your time. I know you have to go, but are there any final remarks you'd like to make with respect to the Conjecture Institute? And in particular, would you like to tell the audience where they can find out more about you and your work and your outreach?
Mm-hmm. Yeah, sure. It's exciting having the Conjecture Institute existing. It's a very, very new organisation, and it's great to have an organisation that's kind of centred around this philosophy of the growth of knowledge. And it'll be fun to see where it goes. And it's nice to be alongside both other physicists and people working on other areas of knowledge within this kind of Conjecture Institute community. My content is kind of on my YouTube channel. I also post on if I'm giving talks and things, I tend to post on LinkedIn if they're coming up. And I'm trying to post a bit more on Instagram as well. That's still an early stage platform for me, I'd say. And then I post on Twitter or X some of my content and comments as well. It's been nice to hear people's questions and try and do my best to respond to them as well. So the other social channels are other ways that you can reach me on YouTube comments or similar things. And thanks for having me on the podcast.
Excellent. Well, we'll put links to all of those places you can find Maria below this video or wherever you are downloading this podcast. Thanks again, Maria. I hope to talk to you again soon.
Yeah,